last Equilib demonstration, we have seen that complex thermodynamic equilibrium calculations are needed for correct calculation of adiabatic flame temperature or concentrations of harmful substances in the products. This demonstration will go significantly beyond those rather simple calculations and will show how the buildup of slag deposits can be avoided when burning coal. Again, we will use the Equilib module of FactSage, since it allows to calculate equilibria under various boundary conditions. We do not want to continue an old calculation, so we select No. We will combine the SGPS database with the GTT oxides database in this demonstration. Therefore, we select No, and the data search window will be automatically opened. As in the last example, we choose the SGTE Pure Substance Database SGPS, which includes an excellent description of pure phases and the gas phase. The GTT Oxides database is provided as unencrypted database, therefore it is available as private database where the user can see all the database content. This is obviously interesting for advanced users who have the background to extend the database if needed. We want to burn coal in the presence of air, which consists of oxygen and nitrogen. As in the last demonstration, we introduced the A or alpha parameter to be able to change the oxygen to coal ratio. The nitrogen to oxygen ratio is fixed in air as 4:1. Before we add the S species, we will have a look at the gas phase composition as function of oxygen to coal ratio. In the menu window, we can see what reactants we entered. We will have to define all the possible products and the calculation conditions. We have selected two databases, therefore we have to manually check the species selection. For this, we right-click on the gas phase. It is immediately visible that there is a problem with selecting all species that are available for the gas phase. The pure oxygen species are highlighted in red. This means that there is more than one entry for these species. We can see that these species exist both in the SGPS and the GT oxides database. If two species with identical name and chemical formula are selected, an error message is shown in the calculation results. Since the SGPS database is designed for a broad field of applications, while GTOX is the more specialized database, it is safe to rely on the GTOX database when there is a conflict. Therefore, we remove the selection for pure oxygen from the SGPS database. We will also do the same check with the solids. As there is no field marked red, we simply work with all solids. When the gas phase interacts with a solid, no matter whether it is housing of the furnace made of steel, a turbine blade made of a superalloy, or ash made of sand adhering to coal, it is useful to get a simple picture of the gas phase composition. For this, we choose a temperature of 1000 degrees C and vary the oxygen to coal ratio from 0.3 to 1.3. in steps of 0.01. As a reminder, an oxygen to coal ratio of 0.5 is needed theoretically to form carbon monoxide, while a value of 1 theoretically leads to formation of carbon dioxide. With the current setting, we therefore mimic combustion under extremely oxygen poor and extremely oxygen rich conditions. Then we start the calculation. We are not interested in the single calculation results, but want to obtain an overview by plotting the activity of oxygen, which is equal to the partial pressure, as a function of oxygen to core ratio. We need to define the axis first. As limits for the logarithm of activity, we choose -30 and 1. The x-axis will be the alpha parameter. That means the oxygen to core ratio. We now have to select the species of which we want to plot the activity. We scroll down until we find oxygen O2 in the gas phase. Then we plot the diagram. As expected, the extreme differences in combustion conditions are immediately visible. The oxygen partial pressure changes over 20 orders of magnitude, so depending on the combustion conditions, extremely different oxygen activities are possible. We will keep that in mind when we now introduce the mineral additions to coal. A typical mineral addition consists mainly of silicon dioxide with significant additions of alumina and iron oxide and small amounts of calcium oxide. Coals typically exhibit mineral additions in the range of 8 weight%. This allows a very convenient way of including the mineral addition to the Equilib calculation. Since 1 mole of carbon weighs 12 grams, as we can see when we move the cursor on the carbon, we can introduce a total of 1 gram of minerals, resulting in a mineral content of 7.7 weight%. As a typical mineral composition, we will work with 0.55 grams of silicon dioxide, 0.2 grams of aluminum oxide and iron oxide, and 0.05 grams of calcium oxide. By specifying the unit, Equilib allows simultaneous definition of reactants in units of moles and grams. Now we move on to the menu window. Since we work with 2 databases, we need to specify which database is more specialized when we select the compound species. Instead of doing this manually, we can use this suppress duplicates option after modifying the priority list. Now, all duplicates will be suppressed from the SGPS database. We repeat this for the pure solids. Then we simply select all solutions that are available in the GTOX database. Information on the solutions, as well as basic information on how they are modeled, can be obtained by clicking. Finally, we will only start with one calculation and thus set alpha to 1. Then we start the calculation. In the results window, we can see that there is, of course, a gas phase, a corundum phase consisting mainly of iron oxide with some dissolved aluminium, a mullite consisting mainly of aluminum oxide and silicon oxide, a spinel that consists mainly of iron oxide, so this is Fe3O4, the other solutions are not stable, so we scroll further down to look at the stoichiometric compounds. There we find cristobalite and anortite. We can see that the liquid oxide melt, that means the slag, was not stable at 1000 degrees C. Slag formation increases particle sticking and can thus lead to deposit buildup. Therefore, we will now calculate at what temperature slag starts to form. We will look at the temperature window of 1000 to 1500 degrees C. With a step size of 50 degrees C, and further calculate all transition temperatures. In the results window, we can immediately see that there are numerous phase transitions between 1200 and 1300 degrees C. We will plot the stable phases now as function of temperature. Since we have inserted 1 gram of minerals, we plot grams on the y-axis and temperature on the x-axis. In the species selection window, we select all stable phases. It is immediately visible that slag starts to form above 1200 degrees C and a pure liquid slag is formed at 1300 degrees C. We will now go back to the results and look at the first transition temperature above 1200 degrees C, since here the liquid slag starts to form. That is at 1225 degrees C. When we scroll down in the results window, we find the slag phase. As can be seen, the amount of slag is still 0. However, the activity is 1. Therefore, 1225 degrees C is the solidus temperature of the mineral addition, and increasing temperature slightly will directly increase the amount of slag. We will now see how the solidus temperature can be directly obtained in a single Equilib calculation. When right-clicking on a phase, several options are displayed. Here, we use the Formation Target Phase option. Since we want to know at what temperature the liquid oxide solution starts to form, we need to leave the temperature field blank. We click on Calculate and immediately get the result we obtained before by doing many calculations in a single calculation. Now we can go back to the menu window and investigate how the temperature for first formation of a liquid phase that can lead to deposit buildup in the reactor is changing with the combustion conditions. That means the oxygen to coal ratio. All we need to do is vary the alpha parameter. For example, between 0.8 and 1.2 with a step size of 0.01. Now we can plot temperature on the x-axis as a function of oxygen to coal ratio alpha on the x-axis. In the diagram, we can immediately see the drastic change in slag formation temperature when changing from oxygen poor to oxygen rich conditions. There is a 200 degrees C increase in slag formation temperature. Thus, the complex thermodynamic equilibrium calculation can be directly used, for example by a power plant operator, to see how operation conditions have to be tuned to avoid deposit buildup when changing the coal and hence the mineral additives. If we want to better understand the reason for the difference in slag formation temperature, we can look at the composition of the slag. Let's have a look at slightly oxygen-poor conditions, for example alpha equals 0.97. We look for the slag and have a look at the composition. The slag consists to 18% of silicon, 13% of iron, 6% of aluminum and 3% of calcium. When we now look at slightly oxygen-rich conditions, meaning for example alpha equals 1.03, we can see that the iron content is reduced from 13% to 8%. Let's plot a graphical representation of how the iron components change in the slag. We will plot mole fraction as a function of alpha. We will select the species in the slag containing iron. There are 10 different components, therefore the plot will be crowded. We will first change the scale of the y-axis to see the results only up to a mole fraction of 0.25. Let's focus on the main 4 components. For oxygen-poor conditions, these are Fe2O4Si, Fe2Si5Al4O18 and Fe2Ca2Si4O12. If we now look at the oxygen-rich side, we see that Fe2O3 is the dominating species. Iron can change the oxidation number, so let's calculate that. In Fe2O4Si, we know that silicon has an oxidation number of +4, while that of oxygen is -2. Therefore, the oxidation number of iron must be +2. The same reasoning can be done for the more complex species, Fe2Si5 aluminum 4O18 and Fe2Ca2Si4O12, and in both cases the result is that iron is present in oxidation state +2. On the other hand, iron is present in oxidation state +3 in Fe2O3, showing that iron in the slag is oxidized when changing from oxygen-poor to oxygen-rich conditions. This change is then responsible for the increased slag formation temperature that we calculated before. To wrap up, we have seen that the oxygen partial pressure changes over 20 orders of magnitude when changing the oxygen to coal ratio. This leads to a change of oxidation state of iron in the melt from +2 to +3. Due to the changing iron oxidation state, the slag formation temperature increases by 200 degrees C when changing from oxygen-poor to oxygen-rich conditions. This understanding allows the power plant operator to change the operation conditions to avoid ash deposits on heat exchangers. This was the second part of the FactSage demonstration. In the next tutorial, the phase diagram module is introduced to calculate binary and ternary phase diagrams. In case of questions, please contact us.